Okay, everybody. Sorry for the late start. I don't know why, but we are starting late. Am I missing anything? I started recording this. Yeah, I am recording it. And am I recording this one? Yeah. Okay, good. Do you guys hear me, online people? Can you hear me?
Yes, sir.
Yes.
Yes.
Okay, thank you. So we have 30 people there. Okay, good. So last week we started talking about operating systems. We tried to define the concept of the operating system, and then we said that instead of defining the operating system, we said that they are okay. The first thing is operating system is a piece of software. That's it. Well, it's a rather large piece, but it's a piece of software. That's what we said, and we said that it is used for two things: abstracting the details of the hardware from the user, so that the programmers can do their programming without paying any attention to the details of the computer hardware, because hardware is something complicated. And the second thing is it manages the software, it manages the resources. What are our resources? Everything on our computer is hardware. Our resources, the most important resource is the CPU, then our memory, then timers, and our disk and mice, and etc. Whatever you have as a hardware on the computer, and software services, maybe they are considered our resources, and it has to be managed. What do we mean by managing? Who is going to use who, what, and who is going to get what kind of share? So that's going to give you the problems about fairness. Okay, I should be fair among the processes. Also, I should be efficient. Okay, I mean, to be fair, I cannot waste 30% of the CPU time, or I cannot waste 30% of the memory. Okay, so I mean, some people say that operating systems are like governments. Devletlere benziyorlar. If you keep the government very large, okay, let's say you have a government, and for a country of 10 million, if you keep a police force of 1 million people, for 10 million people there is 1 million police, okay, police officers, and 500,000 judges and prosecutors, that would be a very safe and very fair country, right? But you are spending 10% of your task force for policing the society and providing the justice to the people. That's too much. I mean, too big governments are bad, but if you don't keep any police officers, then things are going to be out of hand in terms of enforcing the law and providing the justice and etc. So you have to keep the balance. I mean, just to say that you like to make it perfect doesn't mean that as an operating system you are going to get 50% of the CPU or 70% of the memory. You can't do that, okay? So you have to find the balance. Sometimes we have to ignore problems, okay? For example, in our operating systems, do you remember what I said about the deadlocks? Deadlocks are important concepts in the operating system literature in theory, but in practice nobody handles it. Nobody does anything about the deadlock. They just ignore it. They say that if deadlock happens, so it's going to crash the computer. So what is new about it? I mean, computers crash all the time. If I get a deadlock-related crash once every month, that's fine. That's okay, because I have to boot this computer 2 times a week anyway. So that's going to be okay. So that's going to be this. So when I say managing the resources in a sensible way. Okay. So we don't try to be perfect. I mean, there's nothing wrong to be perfect, but if you try to be perfect with the memory management, okay, or the processor management, disk management, then as an operating system you will become your largest software on the computer. As I said before, I am not using this computer to use Windows, right? I am using this computer to project this slide to you. I am using this computer to write things on the screen, and to send email, to browse internet, and that's what I am using this computer. I don't care about what kind of operating system is on it as an end user. Okay, so we talked about this and we moved on, and we talked about the history of the operating systems. That's what we did. And history of the operating systems closely parallels the history of the computers actually. Okay, whenever they put new stuff as hardware on the computers, operating systems have changed. When they made the transistors more available, integrated circuits, very large scale integration, etc., computers have changed. Then they had changed the operating systems too, because now we have more power, more memory, more CPU time. Then why don't I make this fairness thing more practical on our computers, etc. Okay, so the ideas were there. I mean, remember this Multics thing, Multics operating system. Most of the ideas that we use today, okay, it was initiated by this operating system in 1960s, okay, but at that time they didn't have powerful enough hardware to implement all the ideas. Nowadays we have all those ideas and we are implementing it. So idea wise, operating system people, operating system researchers, they did not, okay, they were not short of ideas at all. They had all the ideas long before the hardware is available. Whenever the hardware is available, okay, we started implementing them, most of them. Okay, anyway, so we talked about these, and I'm going to skip those. And I hope you watched the video that I posted on Teams page about the fabric machine, weaving machine. Okay. So then we started talking about the computer hardware. Okay, that's where we left. We said that this course is not about computer hardware. You took hardware courses previously, and we are going to use your knowledge about the hardware a lot. But we need to review the computer hardware so that we can talk about them. I'm not going to teach computer hardware to you, but since as an operating system, we are the software that works closest to the hardware. We need to know about the hardware so that we can manipulate it. We can read data from the hardware. We can write data to the hardware. We can manage the hardware, right? That's what we are going to do. Okay, so we looked at this one. Remember, this is the bus, our main bus. Okay, and CPU is the most important resource and our piece of hardware. CPU is connected to the main bus using the memory management unit. Okay, memory management unit is responsible for translating the virtual addresses to the physical addresses. Okay, as I said last time, let's say I have two processes in my memory. Okay, two processes are running. Each one thinks that okay, this is P1 and this is P2. Each one thinks that starting from address number 000, ending in address number, let's say FFFF, very small address space, they have the whole space for them. Okay, so this one thinks that it owns the space. This one thinks that it owns the space. So this process one says that I like to put this number into this address A02B, and this P2 says that I like to put 32 in there, right? So they can do so. They are executing their own machine code. That's right. But how come I have two different values on the same address? And of course, this P1 and P2 are not exactly seeing the physical addresses. They have their own virtual addresses. Okay, this is a virtual address space for P1, and this is a virtual address for P2. And I can have hundreds of processes like these. Each one thinks that they have their own address space. Okay, but in fact, our MMU is translating each of those virtual addresses into physical addresses. Okay, when that guy says that I am going to write to that space, this MMU says that you are going to write here. The other one is going to write there. Okay, so that's what the MMU does. Of course, it's a piece of hardware, but it has to be programmed. Okay, it has to be programmed, and this MMU has to be said that, okay, now P2 is executing. MMU translates all the addresses from the virtual address to the physical address, knowing that the P2 is executing. And then operating system makes a decision, says that, okay, now P1 is executing. Okay, so operating system programs MMU, and MMU does the translation job for us automatically, but operating system is in the control. Okay, programming this MMU is something privileged. No user programs or the ordinary programs should be able to access MMU, right? It's a very special place. It is you can only access the MMU in the kernel mode or the protected mode, whatever you like to call it. And it is the task of the operating system to modify the MMU flags. Okay, it could be a very complicated MMU. It could be very simplified. For the early computers, microprocessors, for example, there was no such thing as MMU, because the early microprocessors, okay, did not support multiprogramming. Okay, if you like to do the multiprogramming, you have to do it yourself without getting any help from the hardware. But later they supported it. Nowadays, almost all the CPUs, they support this MMU mechanism or the multiprocessing mechanism. So it is the task of the operating system to manage this MMU too, which makes it a little bit more complicated. Okay, so as a regular program, in the user mode, if I try to do something about the MMU, change something about the MMU, okay, the hardware will tell me that I try to execute an illegal instruction, and I'm going to stop you. I'm going to tell the operating system that somebody is trying to execute an illegal instruction. If I try to multiply two register values, that's okay, I can do that as a regular user. But if I try to change something in MMU, then hardware will cause an interrupt. And who's going to handle the interrupt? Operating system, of course. All the interrupts are handled by the operating system. What kind of interrupts, that doesn't matter, because there are types of interrupts. Operating system will handle them. Okay, so we talked about the MMU. In fact, this MMU is the main topic of the chapter number 3 when we talk about the memory virtualization or the virtual memory. Okay, let's go back and let's start talking about one of them one by one. Start with the processor. Okay, it's the brain of the computer, of course. Okay, it has all the necessary hardware for doing arithmetic processing, logical processing, accessing the memory, etc. And you know these 1, 2, 3, 4, sometimes it is 5, 6 steps, but usually it is the fetch cycle, decode, execute, fetch phase, decode phase, execute, and then we repeat all that stuff. Okay, fetch, decode, execute. What is fetch? What does the fetch phase do? It fetches the instructions from the memory, sometimes the data. Decode tries to understand what the instruction is, tries to figure out what part of the CPU I'm going to use to execute this instruction. Then executes it. Then I keep doing this one after the other. The nice thing about this fetch, decode, execute cycle is I can pipeline them. So fetch, decode, execute. Each instruction goes through these 3 steps. Okay, if instruction 1 is doing this, maybe I can do with the instruction 2, I can do fetch, decode, and execute. Since I am decoding instruction 1, my fetch circuitry is available, I can use my fetch circuitry to fetch the instruction number 2. So I am pipelining it. That means what? If I have 3 phases, then it would look like I am executing 3 instructions at the same time. Parallelism, and you have seen examples of this. You have seen problems with this. So this is a pipeline structure is very heavily used in today's modern CPUs, and we are going to talk about them too. Okay, good. And of course, we know that CPUs have registers. We'll talk about them. What are the registers? Registers, let's say this is our CPU. Okay, MMU is part of the CPU nowadays. And we have a set of registers. And registers are usually for 32-bit computers, we have 32 registers. For 64 bits, we have 64 registers. And usually we have register 0, register 1, register 2, up to register 32, let's say. Okay, so registers are simple word storage locations inside our CPU, and they are very, very fast. I can access them without any delay. I can write to them, and I can say, okay, put this one and put this one into my ALU unit to the some arithmetic processing, and the result would be here. I can program this, right? So these are my simple instructions. Add R1 and R2 and put the results back to R17, etc. I can do that kind of stuff. So registers are important. Without the registers, at least for the von Neumann machines, I cannot do anything. What are the other special registers? These are the storage registers. And I have, let me erase these arrows. And I have other kind of special registers. For example, program counter might be the most important register, maybe. Okay, it just tells you where your program is during the execution, right? Program counter keeps remembering my current instruction number for my process. Let's say in my memory, I have 3 programs, process number 1, process number 2, and process number 3. Okay, each one is executing. Of course, since I have a single, this is my memory, this is my CPU. Since I have a single CPU, I can execute only one program at the same time. But what did we say with the multi-programming? It looks like we are executing 3 at the same time. So what happens? While I am executing one of them, the other 2 suspended. They are blocked. They are waiting. Either they are waiting for something to happen, some data, or they are just waiting in the ready queue. They say that I am ready to run, but I don't have the CPU now. So if P1 is running, okay, then the PC points to the execution address. If P1 is running, if P2 is running, then PC points to the execution address of the P2. So the instruction number or the address of the instruction in the memory. What others have? Okay, I have our stack pointer. Okay, you know the importance of the stack, right? Without the stack, it would be very difficult to do recursion. Without the stack, it would be very difficult to do the functions that we know of, right? We keep our local data in our stack, right? Because using stack for the local data is very convenient. Whenever we are done with the local data, whenever we are going to get rid of them, I just move my stack pointer down a little bit. Okay? And someplace in my memory, let's say this is my memory, let's say my stack moves up, it grows this way. So my stack pointer is going to point to that location, and I keep my data A here, then B here, and this here. Let's say I have 3 local variables in my function, A, B, C, and my stack pointer says that you are pointing here, okay? So the position of A is SP minus 0. Position of the B is SP minus 4, let's say these are 4-byte variables, and SP minus 8 is the position for the C. Okay, so stack pointer is so nice. That's why whenever we look at some of the translated assembly versions of our programs, you see this kind of statements, okay, stack pointer minus something, stack pointer minus something. These are the local data. That's why we have this stack pointer, and as you see, it is as important as the program counter, and we have to have a stack pointer for each of our processes, or for each of our running threads. We are going to talk about thread in a few minutes, but let's forget about the threads for now. Let's talk about the processes only. Stack pointers are important, and I have them. And what else? I have program status word. Okay, program status words. It keeps our condition bits, such as the carry. Okay, such as the carry word, or that program stated word keeps information about, am I in the kernel mode, etc. Okay, or is there an exception, like the floating point problems and etc. So program status words keep that kind of information, and it's a special register too. Okay, so that's what we. I mean, of course, this is a very simplified CPU. CPUs are much more complicated than this, but this is the bare minimum of the CPU. Without the registers, without the program counter, stack pointer, program status word, you can't do the most of the stuff that the modern operating systems offer. Okay, let's go back to this picture again. Remember, we have 3 processes running in our CPU, in our program, in our computer. Sorry, operating system has to manage these 3 processes. Well, each one needs the whole CPU, right? When I switch from this P1 to P2, let's say P1 is blocked. Let's say P1 asks the operating system to bring some data from the disk, and it's going to take millions of CPU cycles, so I am not going to wait until the data is available. So operating system says that, okay, you are blocked. Now I am going to let P2 run, let P2 use the CPU. So what's going to happen is that I have to keep all this data someplace safe, so that the P1 does not lose any of these register values, program counter value, stack pointer, program status word, and a programmed MMU values. So I have to save all the data to some place safe in my memory, and I have to then load the data for this P2 from the saved place, so that I can switch from P1 to P2. Okay, so that's what happens when you switch from P1 to P2. You save lots of data and you load lots of data. That's called context switching. Okay. Context switching is something that you need to do to switch from one process to another process, or from sometimes from one thread to another thread. Did everybody sign this? Okay. So context switching is something important. Well, context switching something necessary, but we don't like it much, because why? Why we don't like context switching much?
Efficient.
What?
It's inefficient.
Efficiency. It is expensive, because you have to write all that data to the memory. Okay, you have to write all that data to the memory. Okay, and then you have to load the new ones from the memory, and it's going to take time. So switching from one process to another process is something expensive. You might say that, well, I mean, what is wrong with like loading and saving like 32 registers and at most 50 registers, right? 50 memory references and 50 for the loading them back, 100 memory references. It seems that not much, but MMU is something complicated. Sometimes we have kilobytes of data in MMU. And the most important is that we didn't talk about it, but we have very large part of the CPU is the cache. Okay, especially the level 1 cache. Okay, level 1 cache is something that is specific to the programs, and sometimes, of course, we don't write the whole cache to some place in our memory, but when you switch from one process to another process, your whole cache is invalidated because that cache is not valid anymore, right? I mean, what is the purpose of using the cache? You say that instead of getting the data from the memory, I get it from the cache, because the principle of locality, okay, says that if you access one memory location, it is likely that you are going to access the neighborhood of that memory location. So bring the whole memory location to the cache. But if I switch from one process to another process, this locality goes away. So the cache is invalidated. That means what? I have to invalidate sometimes megabytes of data. Okay? So the cache hit is going to be a lot. Context switching is something we don't like, but we have to live with it. We have to deal with it. So it's not a good idea. It's not a very good idea to switch from one process to another process too often. Okay? You have to let the process use the CPU for some time, then you switch it. Switching is not free. It is very expensive. And it gets more expensive if your CPU is more complicated. Let's say in your pipelining, instead of you have 3 steps, you have 15 steps. That means what? When you switch from one process to another process, you have to sometimes discard all of those running 15 parallel instructions sometimes, and sometimes you have to remember where I left them, and this happens a lot. When your CPU gets complicated, switching becomes more and more expensive. Okay, good. Yes?
I missed the process status word. Can you explain it again?
Program status word? Where do you keep your carry bit? Where do you keep your carry bit? Remember the carry bit? If you add 2 byte values, sometimes you get a carry, right? It has to be kept somewhere. So that carry bit is inside this program status word. Okay? Or when you do a subtraction, where do you keep your equal to bit? Okay? That's where you keep it. It changes from processor to processor. Okay? But those kind of important bits they need to be saved somewhere, and that's the program status word. And let's say this is carry bit, this is equal bit, and this is the kernel mode. If this k bit is 1, then you are in kernel mode. CPU knows that you are the operating system. And if this is 1, I can do whatever I want with the MMU. Okay? So I use that bit as a CPU to mark myself as a kernel or not. So these kind of stuff are in the PSW. Okay, any other questions? Okay, let's go back and let's talk about the switching a little bit more, because I'm going to talk about system call. Okay, so there is a special instruction. In my instruction set in my CPU that makes a system call. Okay, for Intel CPUs it is SYS call. Okay, that's the instruction. Before you execute this instruction, okay, okay, you set values. For example, you put, let's say, 10 to register number 1, 21 to register. So I am passing the parameters to the operating system. Okay. When you say system call, okay, it's called sometimes it's called a software interrupt. Or sometimes it is called trap to the kernel. Okay, you are making a system call to the operating system. You say that, okay, I need the procedure number 10. Okay, and this is my, for example, parameter for procedure number 10. What might be the procedure number 10? Maybe, I don't know, open a file. Okay? What does the open a file need? The file name, access mode, and etc. So you provide all that data in your register and in some special memory location, and you make a system call to the operating system. As soon as you do the system call, this kernel bit is set to 1. Now the CPU is in the kernel mode, and actually the operating system is now handling the interrupt, the software interrupt. Okay, so you are letting the operating system handle everything for you. Now the operating system starts using the CPU. Operating system has the control, and operating system is in the, of course, kernel mode. But operating system is not magic. Okay, it's a program as simple as a program, only running in the privilege mode. It has to use all this data, all this structure. So it has to use all these registers, but as a process I was using them, I don't want to lose all that data in my register, so the operating system saves all this data. So it's kind of a context switch from the process to the operating system, right? So making a system call is something expensive too, because you are saving all this data. You are saving all this data to some special place. So operating system calls you are making to the operating system is expensive because you need to switch from the user mode to the kernel mode. This switching, you might think that, well, it is as simple as making this kernel bit from 0 to 1. That includes it, but on top of it, you need to save lots of data. And operating system, as a program runs it, of course, it needs to use this CPU data, CPU registers, and all that kind of data included in the CPU. I have to save them, and if the operating system thinks that there are other things that I need to do, it does them too. So it's kind of a context switch from the process to the operating system. When the operating system is done, for example, I said that I need this data. Okay, I'm opening this file. Whenever the file is opened, okay, I'm going to continue, right? Well, opening a file takes a time because, especially if I have a mechanical drive, mechanical drives are so slow compared to the CPU. My process is going to be blocked for a while, and operating system says that, okay, I cannot go back to this process number 1 anymore because it's going to be blocked for a while. I'm going to let P2 start again. So it's going to be context switch from the operating system context to the P2 context. So these kind of things are happening all the time when you do the operating system call, Okay, it's a special instruction that causes software interrupt or kernel trap to the kernel. Okay, and we will keep talking about it because with the process management, this context switch time will come into picture a lot. We will talk about this context switch time, and we will try to make this context switching less and less often. Okay, any questions?
Hocam,
Yes.
is this the reason why when we make 2 file operations at the same time they are slower?
Two what operations again?
File operations, like copying files.
They are closed. What do
Copying
you?
files.
Okay. You are trying to do file operations 2 at the same time.
Yes.
How can you do it at the same time?
Yeah. For example, I copy one folder has 10,000 files in it, and at the same time while the other operation is running, I make another folder to copy.
You are talking about as a user, not as a programmer. Is that what you are saying?
Yes.
So when you do this, if you have a slow computer, it's going to take a lot of time. I don't understand your question. Are you telling me that why is this taking so long if you do it at the same time?
Yes.
Well, I mean, you are trying to use the same resource 2 times. It is the disk. If you like to do, okay, that's a good question. This is your operating system, and this is your disk, okay? And let's say you have 2 programs, P1 and P2. Both of them are trying to use the disk at the same time. Well, of course, nothing happens at the same time, but virtually at the same time. So one of them is trying to move these files from this location to this location. The other one is trying to move these files from this location to this location. Okay? And if I try to do the same thing at the same time, so what am I going to do? The operating system is going to produce a sequence of control commands, like lots of command number 1, command number 3, 2, 3, 4, 5, 6, etc. to the disk. And the disk has to execute all of them. At the end, if I execute them, all of mine will be moved from this location to this location and from this location to this location. I know that. But the disk has mechanical structure in it. It cannot handle all of them in a very efficient and fast way. And if I keep switching between these operations and these operations, let me show you the structure of the mechanical desk. Where is my desk? Okay. So I have this spindle. Okay, this is like a axe. Okay, around this axe, around the shaft, the disk is spinning very fast. And these are my read-write heads. They can move in and they can move out. If my files are under these locations, then I don't have to move my disk heads in or out. I can stay in there. But if my second set of files are here, let me make it green, okay, here, like that, okay. Whenever I need to do something between those two, I have to move these heads forward and backward, and that's going to take time. So maybe it is more logical to, maybe it is more reasonable to do the blue file processing first, then the green ones. But since you ask me to do them at the same time, this mechanical drive will try to do all those processing by interleaving the commands between themselves. So at the end, I will move my files, but because of these mechanical constraints, at the end, it's going to take a lot of time. Usually, that's the reason. I mean, it is the reason why we have these kind of delays if I do two things at the same time on my mechanical disk. But this is not just because it is the mechanical disk. Sometimes I have to okay, sometimes I have to do this kind of stuff between the memory too. Well, if I keep switching between the processes, okay, process 1 and process 2, and if I don't have enough memory, then those kind of delays will happen too. Because what did I say? This memory for P1 and this memory for P2 and P3, if you add them up, they are much larger than my whole physical memory, right? They don't fit in my memory. When I switch from P1 to P2, so where does the memory for the P2 come from? I have to save this whole data to the disk, okay, because I don't have enough memory for P2, and I have to load this data from the disk to the memory again. So context switching sometimes requires me to write some data to the disk and load some data back from the disk. So sometimes it gets way more expensive than that I told you. So sometimes if you do more stuff at the same time, these kind of delays will happen. Okay? So basically, the answer to your question is yes. That's why it's happening. It's not because the disk thing. It is because if you don't have enough memory, if you don't have enough cache space, or if your I/O devices are slow, then those kind of things will happen. Yeah. I mean, if I run process 1 by itself, and if it takes 3 seconds, and if I run process 2 by itself, okay, the whole owner of the computer is process 1, it is 3 seconds. Whole owner of the process 2 computer is the process 2, it takes 5 seconds. But if I like to do P1 and P2 at the same time, okay, this will get sometimes 12 seconds because of these context switching between them. Okay, and this is called trashing. Trashing. Okay. Trashing is the process of unnecessarily loading data from the disk and writing back to the disk, and this happens when you don't have enough memory. Okay, and operating systems have ways of dealing with the trashing. I'm going to show you my memory structure again. Okay, so it says that where is my memory? Yeah, so I have 13% memory available. Okay, you might say that why? Well, I mean, I have hundreds of processes running on this. Okay, if I add up all the memory requirements of those processes, it will be maybe 50 times more than my currently available physical memory. Yet I have 13% of my memory is available, right? Why does the CPU, why does the operating system keep that 13% available? It is because if I keep that 13% available, it's going to be easy for me to switch from one process to another one, because I don't have to write some data to the disk. I can immediately load it from the disk. So keep some memory always available. Otherwise, this computer is going to be way more slower than now it is. It looks like I am killing this computer. I don't know. I mean, just turn off some stuff. Am I using Chrome? It says Chrome is using some. No, it is not using anything. Who is killing me? Robert. It's using lots of memory, right? Yeah, it's using lots of memory. My CPU is OBS. Well, anyway, I paid lots of money to this computer. Okay, let's let it run. Okay, so good. Any other questions? So we will talk about. I mean, this kernel mode system call are important, and we are going to talk about it a lot. As I said, I mean, this whole course is about system call actually. System call is how you switch to the kernel mode. What did I say? When we say the operating system, for us the operating system is a part of the operating system that runs in the kernel mode. Okay. How do you run from the user mode to the switch from user mode to the kernel mode? Is the system call. You make a system call, and operating system handles it. Okay. We talked about the CPU pipelining before. Fetch, decode, and execute, 3 phases of the whole instruction execution cycle. Okay, these are the classical structure for the pipeline CPUs, but nowadays we have these kind of CPUs. These are called superscalar CPUs. Okay, superscalar CPUs, and you have more than one fetch unit, you have more than one decode unit, and you have many copies of the execution unit. So pipelining with this kind of structure is way more complicated. If you do it right, it is much more efficient than the classical pipelining. Okay, it looks like I can do 1, 2, 3, 4, 5, 6, 7, 8 instructions. I can handle 8 instructions at most at the same time. So 8-way parallelism. That's a loss of efficiency, right? That's a good thing. But who is going to handle all these complications? Hardware plus the operating system. Okay, when I'm using this one, if an interrupt happens, okay, when I'm using this structure, if an interrupt happens, I have to save all that data. Okay, and the bad thing is that I am in the middle of executing something. Okay, saving the CPU, all those registers, and it's not going to be enough. I have to save the state of the CPU like that one. Okay, for instruction number one, it was decoding the instruction. Instruction number 2 was fetching it. Instruction number 3 was executing it. If I like to save all that data, and whenever I am coming back, I'm going to continue. I reload that kind of data, processing all that data. Of course, hardware helps me a lot, but as an operating system, it's my problem. Okay, so the superscalar structure is good for the, of course, for the whole efficiency of the whole computer, but operating systems will get complicated to handle this kind of structure. Okay, let's talk about the multi-threading and multi-core cores. Okay, but it looks like maybe I need to take some break since we are so crowded. Maybe I shouldn't be. Well, I started late anyway, but okay. So let's take 15 minutes of break. Let's be here around 11:37. Please open the windows.
Hocam ismimi eklememiştim ama size sormadan imza atmayayım dedim ama
Eklemedin mi?
Excel'de eklememiştim. Üstüne yazmayayım dedim ama sizin bilginiz olmadan. Bilimsel hazırlık öğrencisiyim.
Nereye yazıyorsun anlamadım.
Ben şuraya ekleyeyim mi yani?
Hayır tabii de ekleyemezsin. Sen olamazsın sen. Sınıfta foto var. Virüsten dolayı 70 kişiden fazla almıyor. Hocam sen kayıt olmadan gelemezsin.
Yok derse kayıtlıyım hocam.
Hayır kayıtlı değilsin.
buraya-
Kayıtlı olsan burada ismin olmazdı. Her akşam, her pazartesi, pazar akşam oluyor.
Kontrol ettim ama daha yeni işte fark ettim. Bir de hocam size ben mail atmıştım hani.
Neyi fark ettin anlamadım. Sen geçen hafta derslere gelmedin mi?
Online katıldım hocam ben derslere.
Söylediklerini duymadın mı?
Yani ekleyeceğimi biliyordum ama bir öncekine ekledim ama gelememiştim. Buna da hani
Tamam onu yok saydık. O olmadı tamam mı? Ne yaptın bana e-mailde?
gelmem sıkıntı oluyor demiştim hani hem çalışıyorum işte hem de İstanbul'da ikamet ediyorum hani online katılsam olur mu demiştiniz bütün derslere.
Evet.
Siz de hani gelmem lazım demiştiniz hani bir gün.
Şu
O
sınıfın
yüzden-
yarısı İstanbul'da oturuyor, 1/3'de çalışıyor.
Yok doğrudur hocam. Öyle de hani şu an imza atabilseydim iyiydi.
Bekle.
Şantor deneyince yolu Sana okul çalar ya. Yok mu? Okulda. Bizimkiler bir şeyler var.
İyi seyahatler hocam.
Üzerinde gelen startup şirketin de var. Yani hem Sakarya'da açtı hem de Kocaeli'de açtı. Sakarya'daki boş. Hayvan şirketi. Cidden para var. Gerçekten para var. Yani TÜBİTAK projesine başvuruyor şirketle. Kendi şirket. Asıl şirket. Ayrı bir şirket değil, o şirketle şey yapıyor. Başvuru yapıyor. Proje iletiyor. Proje kabul alıyor. Resmi alıyor. Hem de faktan yer alıyor. Hem de vergiden doğal.
Şey bir şirket de değil yani.
Böyle yaşıyorlar artık. Geçen seneyi peki yaptılar. Gayet öyle yani. Çok da iyi. Dada'da şey yok değil mi? Geçen öyle yapıyor. Öyle mi değil mi? Almıyor mu? Aa, bu tek çok almıyor. Yine ne almıyor? Bir şuraya bak. Üstteki ileri yapmışlar. Onlar işte.
Başka yere
Bir şuradaki
düşünmüşsün bulamadım.
orası konteyner.
100 liraya
Pimbayı kopyalım. Şöyle bir
Kim de vardı onu da bilmiyorum. Kendi filmini taktı mı benim? Kendi filmini taktı yani.
binanın içine ofis yapmışlar. Pencere koridora bakıyor. Yani şuraya pencere düşün, koridora bakıyor.
Evet bakıyor abi. Yapsaysa da abi.
Bir tane daha tavanda bir pencere gibi bir şey var. Tepe bir şey ama ışık geliyor ama şey, buzlu böyle.
Dediğim ki o
Gökyüzünü göremiyorum.
Tasarım var, eğitim var, şey, dokümantasyon falan.
Öğrenci. Oradan şurası ona
Güzel oluyor, şimdi okul başlayınca bırak. Abi bir arkadaşım var, başka şu an yapıyorlar da.
Başarılı belli olur.
Zaten çocuk bir ben ayarlar cam açık kalsın. Yoldan güzel gidiyoruz ama buna gitti der. Tamam, sıkıntı yok.
Tutamadık sanki. 10 aldı hani. 50 alsan sınır var mı orada şu kadar alacağın bir ortalama?
Okay, so we said that we are going to assume that we have only a single CPU on our computer, and the operating system is responsible for managing this single CPU. But in reality nowadays, you can't buy a CPU with a single core. Most of the CPUs, they come with multiple cores, tens of cores. So we have to talk about this a little bit. And we need to make some terminology definitions about multi-cores. Multi-core CPU means that on a single chip, they put more than one CPU. That's as simple as this. For example, you call this a single chip, okay? When you buy an AMD CPU chip or Intel CPU chip, there are in this case 4 different CPUs. There are really 4 different CPUs. And each one has its own registers. Each one has its own stack pointer, program status word, and etc. And each one has its own L1 cache. Okay, L1 cache and L1 cache. Here are the L1 caches. Okay, so why do they make 4 cores on the same CPU, on the same chip? Because it is easy to produce it this way, okay? Instead of making 4 different chips and putting them side by side, it is less expensive to produce them into a single package, okay? Put them into the same slot, and handle it that way is much cheaper than putting 4 different CPUs on the same board. So this is more economically feasible. You can share some data between these CPUs through the L2 cache. L2 cache is L1 cache is much faster than L2 cache, and L2 cache is much faster than your main memory. So these 4 cores, they share this L2 cache structure, okay, hardware. Sometimes it is organized this way. L1 cache and L2 cache are on the same core and they are not shared, but sometimes they are shared. Sharing is sometimes good, sometimes bad. It is good because it's very easy to communicate between these, okay? It is good that way, but sometimes it is bad. Why? Because you have to keep the copies of the same thing in different places. So there are pluses and disadvantages. So most of the time, whenever you buy a computer, whenever you buy a CPU chip nowadays, there are usually more than one CPU available on that chip. So who is responsible to manage all those cores? Of course, it is the operating system, but sometimes it is the program too. I mean, when you are writing a program, if you know that your program is run on a multi-core CPU, okay, maybe you can take advantage of it. For example, if you are doing something that can be parallelized, you will say that I have 2 things to do. I am going to run them in parallel. One is going to do this, the other one is going to do that. And as a programmer, you know that you are doing 2 things at the same time. Okay, this multi-core thing, supporting more than one CPU at the same time on your computer, is because of this Moore's law. You know the Moore's law, starting from 1970s. This guy, one of the founders of Intel, okay, he said that at about 2 years, and every 2 years, okay, we will have 2 times more transistors on our chips. Okay, if you give me $1, you are going to buy 2 times more transistors for the same dollar in 2 years, and that's what have been happening. Okay, we used this law until the 2010s or 2000s. Okay, to make the CPUs more super scalars, more cache, okay, better instruction set, and etc. But it got out of hand. Nowadays they are using these neat transistors, to put more CPUs on the same chip. Okay, that's what's happening. That's what is happening nowadays, and it's going to continue. And I mean, they say that, okay, when I was an undergraduate student in 1990s, okay, they say that Moore law has maybe a few more years to live. After that, it's going to die. When 2000s came, again they said the same thing. 2010s, and nowadays 2020s, it still continues. And if you look at this, Wikipedia, I think I looked this up this morning, and it was from the Wikipedia, yeah. It was a nice example, yeah, I think, yep. Transistor counts starting from 1970s, okay. So that guy said that when they launched this 4004, okay, this was the number of transistors they were able to put on a chip. This was an extraordinary number, 1,000 transistors on a chip. So you are talking about ENIAC kind of machine on a single chip from 1950 to 1970, okay? And he said that it looks like we are going to double our number of transistors on a single chip every 2 years, okay? When 1970, it is 4,000 now. It goes like that, and nowadays we are talking about 50 billion transistors, okay? I remember this date. I remember this one, 486, okay? This was the first time they put more than 1 million transistors on a single chip, and then we hit this number. I remember this one, but I don't remember this one because it was so crowded there. So which one was the first one? I think many of them. Yeah, quad-core GPUs. So that's the 1 billion. Now we are talking about 50 billion transistors on a single chip. Nobody hit that down, but I mean, you know, it's going to be hit in a few months. Is this? Yeah, maybe we hit it. I don't know. This looks like this is 2 years old. Okay, so Marlowe says that more transistors are going to be available on your chip. Okay, so nowadays it's more logical to put many cores on the same CPU chip, and somebody has to handle as software. Somebody has to handle all those. So on this machine, I don't know how many. I think I have 4 cores maybe, and my cores, there should be a way of seeing. Okay, this is my CPU. This is total CPU. There should be a There should be a way of seeing what each core is doing, but I couldn't. Maybe this one? Did I open my... It says open the resource monitor. Where is my resource monitor? Is this my resource monitor? Yeah, here it is. Yeah. I think, yeah, okay, here it is. So this is my CPU. Yeah, CPU. There should be one way of seeing what each of my CPUs are doing. Yeah, here it is. Okay. CPU number 0, 1, 2, and 3. Operating system, of course, knows which process is running on which CPU because it allocates it. So obviously this is a multiprocessor operating system. Whenever it needs to run something, so it is doing the scheduling on the same CPU and on the different CPUs. So you are going to run on this CPU and you are going to run on this CPU. It looks like I am running all these processes on different CPUs. See, this one is running on CPU number 1 and this one is running on CPU number... What is this 31? I don't know what this is. Okay. Is there a mistake? So most of them are. Let me sort it with respect to CPUs. A virtual CPU number of CPUs. I don't know what that number is really. I thought that I had only 4 CPUs on that, or maybe the virtual CPUs. Oh, okay. I need to look this up. I don't know why this number is up. I think it is the number of virtual CPUs it is using. I don't know. So the operating system has to deal with these kind of complications. So let me close these, all of them. Okay, so these kind of operating systems, this Windows operating system or the any other modern desktop operating system, they are very, very advanced. They came a very long way. I mean, using all those processes, trying to run many processes at the same time, managing all those CPUs, and still staying interactive is something very, very interesting, very, very difficult. Okay. And like 20 years ago, these kind of things on a hardware like this wasn't possible at all. So let's talk about this multi-threading. Okay, what did we say? We said that switching from one process to another process is something expensive. Okay, we said that. Okay, because you have to save all this data. I mean, saving the registers, saving the program counter, stack pointer is something inexpensive compared to dealing with the complications of the MMU and the cache and etc. Okay, so it takes more time to deal with the cache hits and the MMUs. Okay, it is more difficult to handle all these kind of. It's not difficult. It takes more time. So somebody said that why don't we write threads? Threads are kind of lightweight processes. Okay, so we are going to share our address space. Okay, I am going to say that this is my memory. Okay, for this memory there is this process 1. Inside this process 1 I have 2 executions, thread 1 and thread 2. Okay, these thread 1 and thread 2 is part of process 1. I am running 2 different programs, if you like to call it that way, inside this program number 1, but they are sharing the same address space. Okay, so if T1 modifies a memory location, T2 can see it. So they are modifying they can modify each other's memory positions. So that means what? They are sharing the same address space. Their virtual memory is the same. If I switch from T1 to T2, I don't have to update the MMU. I don't have to get the cache hit at all. So switching from one thread to another thread is much less expensive than switching from one process to another process. So they have invented this in 1980s, maybe 1990s, I guess, and they called it lightweight processes, the threads. So threads are parts of programs or the processes, and threads share lots of stuff between themselves, like the MMU structure and the cache structure and everything. And switching from one thread to another thread is much easy. So what is the downside? They can see each other's data. But that's okay, because usually the same programmer writes the thread for T1 and thread for the T2. So let's say I have the word processing program like the Microsoft Word. Okay, in Microsoft Word I decided that I have 3 threads. This is a classical example actually. Thread number 1 is responsible for reading and writing to the desk. Thread number 2 is responsible for interacting with the user with the keyboards and the mouse and the screen. And let's say thread number 3 is responsible for spell checking. They are running in parallel. Okay, of course they have to see each other's memory. Of course they have to communicate with each other. So it is perfect. So I write 3 different threads for my word processor, and it works very nicely. So another way of multi-programming, and we use this idea a lot, and we are going to talk about threading, multi-threading, when we talk about the processes in our next chapter. So why am I talking about the multi-threading when we talk about the multi-cores? Because our CPUs, they support multi-threading. Okay, they support multi-threading. How do they support multi-threading? They support it this way. Okay, they say that I am going to give you 4 sets of registers, okay, for your CPU. Okay, so that means what? 4 copies of registers are available for me to use. So thread number 1 are going to use the first copy, then the second copy, third copy, and fourth copy. Okay, 4 different copies of the register set is available, and I can modify each one of them. So switching from one thread to another thread simply means that, okay, I'm going to use the second register copy. Okay, I'm going to use the third register set, the fourth register set, etc. So switching is very, very cheap. In a single clock cycle, I can switch from one thread to another thread without getting affected from the context switching. Okay. Of course, I am not switching from one address space to another address space. This is much simpler and much cheaper than process switching. Context hit time is much less severe than the context switch time of the processes. Good. As I said, we are going to talk about it a lot when we come to processes in our chapter number 2, multi-threading. Good. Okay. So we talked about this. So again, let's not forget what we are doing here. Okay, I am going to say this a lot. I talked about the CPUs. Now I'm going to talk about the memory. Then I am going to talk about the IO devices later. Let's talk about the memory. Okay, so we are talking about the hardware, underlying hardware aspects of the operating systems. We like our memory fast, we like our memory large, and we like them cheap. But unfortunately, you cannot get all 3 at the same time. It is not possible to get fast, large, and cheap. Okay, not all possible with any technology. So what are you going to do? You will have this kind of hierarchy. If you like to go fast, you have registers. But registers are expensive and they are not large. Okay? If you like to get large, you use your disk or magnetic tape. Well, they are very, very large and cheap, but they are not fast. Okay? So we have this hierarchy. This is a classical hierarchy. Okay? So what are you going to do? You keep moving your data in this hierarchy. Okay? If the registers are not large enough to keep your data, then you use your cache. If it is not large enough, then you use your main memory. So you keep moving your data up and down in this hierarchy. Okay? So you keep copying it. Okay, from the cache to the registers, from cache to main memory, and from main memory to the disk. That's what you do. And who is going to manage all this movement? Of course, the operating system with the help of the hardware. Okay, these numbers are kind of maybe 5-10 years old. Okay, doesn't matter these numbers. I mean, you just add a 0 next to them for every 10 years. That's okay. But the picture stays the same. By the way, these magnetic disks are going away, and nobody uses the magnetic tapes anymore. Instead of having the magnetic disk, we have the solid state drives, right? SSDs. So I keep changing their names. Okay, maybe the access times they change a little bit, but okay. So these are kind of the reference times. For register access, you need to spend 1 nanosecond. Okay, remember this is seconds, milliseconds, okay, microseconds, and nanoseconds. Okay, this is. Can you read these? No, I can't. Use the blue. Okay, I have seconds. I have milliseconds, 10 to the minus 3. I have microseconds, 10 to the minus 6. I have nanoseconds, 10 to the minus 9. Okay, and this is 10 to the. Okay, so just 1 second. So 1 nanosecond is the register access time. Cache is like 2 times more. Main memory is going to be 10 times more time to access. Magnetic disk, you see the difference between them? It's like infinity, like it's like 10 nanoseconds and 10 it is 10 milliseconds. It's like it is not microseconds, it's milliseconds. It's like lots of time. Nowadays, this gap is getting closer because we are using the solid state drives. It is not mechanical, but the difference is a lot. And I think this picture is a nice picture. Latency numbers. Latency numbers. So we are 1 nanosecond. L1 cache reference takes half a nanosecond. Okay. L2 cache reference is 7 nanoseconds. Okay. Main memory reference is 100 nanoseconds. So it looks like it is 100 times more time to access your main memory than the registers. Okay, what else? Let's see what kind of numbers we have to access the... So, SSD random read, 1 gigabytes SSD, it is 150 microseconds. So this seek time, is mechanical disk seek time, is moving your disk head from one location to another location. It takes 10 milliseconds. Okay, 10 milliseconds, 10 to the minus 3, and to access a memory or register it is 1 to the minus 9. Okay, so it is million times slower than accessing your registers. Okay, so I mean, these kind of things are kind of, I mean, obviously the number change, but the important thing is the ratio of the numbers here. So if you make a mistake of going to the disk to get some data in your program unnecessarily, that's going to be that means that you are going to be penalized a million times. Then you are doing the same thing for the memory when you are writing programs. So going to the disk is always expensive. And what did I say? Sometimes you switch from one process to another process. You have to load all the data from the disk because there is not much space on your memory. Then context switch time is going to be very, very, very, very expensive. Okay, so this one is good too. This one talks about again in terms of times. So 10 to the 0 CPU cycles. Okay, simple register operations, they are just one CPU cycle. Okay, but if you are doing let's say L1 cache read, it is 340 CPU cycles. L2 is 12 CPU cycles. How about the division called integer memory, main memory read? Okay, it is 100 cycles. If you don't have that data on your cache, and all these numbers, they talk about doing stuff if the data is available in your cache. Look at this one. Okay, C function direct call takes 15 to 30 cycles, but if you are doing a virtual function call, it takes up to 2 times more CPU cycles. Okay, exceptions. Okay, remember what I said about exceptions? Exceptions are only used for exceptional cases only. If you are doing the same thing over and over again, it's like 10,000 memory CPU cycles to handle an exception. Okay, and thread context switch total cost. Okay, up to 1 million cycles when you do the context switch. Okay, what can you tell me what is the difference between this line and this line, or maybe this line and this line? It looks like the difference is 2,000 cycles versus the 1 million cycles. Both of them are talking about thread context switch. It looks like directly it is just 2000 cycles, not much. But if you, well, it says that it's using cache invalidation. But maybe somebody should explain it explicitly. What do we mean by cache invalidation?
You need to retrieve data from the disk, so it could take more.
No, this doesn't talk about disk. If you go to disk, we are talking about billions, not millions. We are not talking about disks at all in this picture. What is cache invalidation? What was the basic principle of caches?
And data is ready, maybe?
Who is talking what?
Space locality.
What?
Maybe when data is ready, when there is no misses.
Say it again louder.
Maybe that maybe it takes 2000 these millis if there is no misses on the cache, and if there is much more time.
But why do we have this miss problem when we do the context switching?
Because another process is using the memory.
Because you lose what? What is the main principle of cache?
Locality.
Principle of locality. You use the locality, right? When you switch from one thread to another thread, you are using the same address space, but you are running a different program now. Okay, you are going to use your locality most of the time, so that's going to give you lots of cache misses. Those cache misses will cause you up to 1 million. So if you are lucky, it's going to be just 10,000. Okay, if you are lucky, it's going to be just 10,000. Then in this slide, I don't talk about the context switch time between the processes. This is the context switch time between. Okay, kernel call means system call. Switching from the user mode to the kernel mode, it will take you 1,000 cycles. Okay, because you have to save data, as I said. And this one doesn't talk about the cache hits either. Okay, good. So these kind of things are available all over the internet. Just download them, look at them, try to understand what's going on. Okay, try to make sense of them. Good, I talked about this. So memory is something that we are going to deal. So we are going to spend at least 3 weeks about memory. Simple types of memory. We wish that everything is like registers. Okay, they are very simple. They have their names and you access them. They are very, very fast. Unfortunately, you cannot make them very large because they are expensive. That means that, I mean, to add a new register to your registers is changing the whole CPU structure, changing the whole architecture of the CPU. So, I mean, to add more registers to your CPU, you have to switch from 32-bit computers to CPUs to 64-bit CPUs, right? So, for 32-bit CPUs, we have 32 registers usually. For 64-bit systems, we have 64 registers. Okay, but it took us maybe 15-20 years to switch from 32-bit CPUs to 64-bit CPUs because it takes time to add all that kind of transistors to that CPU. It is not that easy. Okay, but the nice thing is that no delay accessing them. Okay, in a single instruction, you can access more than one register, add R1 to R2, and store the result into R3. So I'm accessing 3 of them at the same time. So that's okay. So if you don't have enough space in your register, then the data, you are lucky if the data is in the cache. So L1 caches, we are talking about kilobytes. And for the L2 caches, we are talking about the megabytes. And L1 cache is, of course, a few times faster than the L2 cache. And L2 cache is more than 10 times faster than the main memory. Okay, so this registers and cache are this part. Your program, your assembly program knows about the registers because it knows the name, but it doesn't know about the cache, right? So your program talks about the registers. It says that add want to register number 1. You can say that. But you cannot say that I am going to get this number from cache number 1 or cache number 2, level 1, level 2. No, right? So you don't know about your cache. You know about your memory, of course. You will say that I am going to access address number this. That's okay. So who handles this cache mechanism in that case? Operating system and the hardware. Mostly hardware though. Okay. Hardware handles it. Hardware says that if the location in your memory is available in the cache, I am going to use it in the cache. Otherwise, I am going to go to the main memory. That's going to be the cache processing, and you already know about that from your hardware courses. Okay. So these kind of questions are all questions that needs to be answered by somebody, either operating system or the hardware. So when to put a new item into the cache, when should I load that data to the cache, okay, and where should I put it, okay? If the space is not available in my cache, how should I remove it? Okay, which one should I remove it? And what are the algorithms for these? And usually these are all handled by the hardware. Sometimes with the risk structure, okay. The main philosophy of the risk structure, what is risk?
Reduced instruction set computer.
Say it louder.
Reduced instruction set computer.
Okay, did everybody hear it? No, nobody heard it. Reduced instruction set computers. The opposing structure is complex instruction set computers. Okay, reduced instruction set computers say that don't implement much on hardware. Okay, if you have an algorithm, then that algorithm should be implemented in software, so that makes your CPUs much simpler. Well, simpler doesn't mean that less number of transistors. You are going to put the same number of transistors, but I am going to use those transistors for larger cache or more number of registers. Okay, so for some RISC machines, these kind of things are done in software too with the operating system. Okay, complex instruction set computers, they just do the opposite. They try to implement more in hardware, so the hardware will help you a lot. Your operating systems gets lighter, okay, because most of the things are handled by the hardware. But some people say that I cannot take advantage of the software anymore. I mean, if I have a new technique to make the cache more efficient, well, I mean, for the CSE computers, I can't do that because it is all in hardware. I cannot change it. Okay, for the RISC, it will be optimized. Okay. It will be optimized. Smart RISC architecture plus the smart compilers. We learned it in 1990s and 2000s. Okay, we learned that it is much better than making your hardware CPU complicated. Okay, very smart compilers. Compiler knows the structure of the RISC architecture. Okay, it optimizes code for that processor only, and your software just flies. It runs much faster than the corresponding CSE part. Okay, disks are larger, they are cheaper, and of course they are slower than the main memory. Slow because they are mechanical, but nowadays they are not that much mechanical. I mean, if you buy a new computer, most of the time they come with the solid-state drives, but they are again slow. Okay, do you know why solid-state drives are slower than the main memory? Well, they are using almost the same technology, maybe. I mean, there is nothing mechanical in an SSD. Okay, solid-state drive. There is nothing mechanical in an SSD, but still they are slower than your main memory. Way smaller than your main memory. Do you know why?
They are so big.
They are?
Large size. Their size are so big.
They are much larger than the main memory,
Yes.
but that doesn't make them slow. Large doesn't mean slow.
Maybe the buses that are connected to it are.
Say it again.
The buses connected to it might be.
Exactly. Did everybody hear it? Of course not. Nobody hears you other than me. It is this, okay? Remember what I drew last week, okay? There is a special bus between CPU and the memory, okay? So the memory and the CPU can communicate in a very, very fast way, okay? But my SSD drive is connected to this controller, okay? I have to communicate through this bus, and this bus is much slower than this bus, okay? That's one of the reasons. That's not the only reason, but that's one of the reasons why SSDs are slower than the memory, okay? And of course, the SSDs are the flash memories. They are supposed to keep the data when the power is off. Memories are not designed that way. When the power is off, all the data is gone. So their technologies are different, but I mean the fact that the hard drives are slow from the memory is because they are mechanical and because of this interface. Because of this interface. Okay? So again, I have this hierarchy. What? Do I have enough time? No, I should use it. I should use my power. So this hierarchy is still there. It won't go away. The relations, the ratios might change, the numbers might change, but registers will always be faster than your disks, your SSDs. Okay, and they will be they will be smaller. Okay, good. I think it's a good place to stop at. No, well, let's talk about this disk, and then we're going to stop. Okay, they are larger, cheaper, and slower. Slow because sometimes they are mechanical. Slow because of the bus problems. And we keep our operating systems and applications on the disk because memory, the content of the memory will be gone when the power is off. Okay, since disks are large, that doesn't mean that we waste space. Of course, we have to be very careful. Space is not enough. Okay. It is always there is I mean this is the case. It is always you are going to run out of your memory, you are going to run out of your registers, you are going to run out of your disk space, you are going to run out of your bandwidth, etc. Okay, this space or the resources are never enough. As we human beings, we keep wasting stuff. We waste everything. Okay, so we do the same thing for the computer resources too. So somebody has to. What's going on? What did it say? I am giving you power. Okay. So we have to be careful. So who is going to manage the disk space? It is the operating system. Okay. So what are we going to do that? Well, I mean, disk is organized like the memory. It's very similar. How is the memory organized? Address number 0, address number F, whatever. And disk is the same thing. Only these numbers are much larger. But I need to keep the data on the disk. I have my files, I have my directory structure, I have the ownership stuff, I have some system files, I have some backup problems. An operating system is responsible for managing all that data. Naming the files, putting the directories, and making the links between the files and directories and ownership, etc., protection stuff. Operating system does that, okay? This space allocation, file names, protection for files, they are all the tasks of the operating system. And when we come to the I/O chapter or the file system chapter, we will talk about disks. Okay, so I think I gave you this example. I mean, this is an interesting picture, but it's going to, I think, in a few years, we are not going to talk about this anymore because disks are going away. But anyway, so, and then after that, we are going to talk about this I/O devices, but it looks like I don't have time for this. Next, tomorrow, I will talk about this I/O devices, and I will try to finish up with this chapter, and then we will start talking about the then we will start talking about the processors, CPU. Okay, that's it for today. Efendim? Sen şu an dersteyim. O da kırılmasın ama. Tamam. Aha. İyi tamam. Aha. Bilmiyorum ki ya. Bir dakika dursana ya. Ben dersteyim ya. 5 dakika, 5 dakika. Size de arkadaşlar yine gelin, beklerim her zaman. Ama imza atmadan şey atmadan gelmeyin, tamam.
Hocam derse ismi yazmayı unuttum. Geldim, online'da katılamadım. Yok yazıldım. Yapılacak bir şey yok diyorsunuz.
Niye olmasın? Gelecek derse gel.
Tamam, yarın da geleceğim ama gelemeyeceğim işte. Sıkıntı yok.
Tamam, artık kocaman adamsınız. Ayarlayın o işi. Ne diyeyim ben sana?
Şeyde, burada sizin gösterdiğiniz yani bastığı bir tane şey var ya. Bu
Ne var?
slaytta. Bas var.